Today we're going to be looking at friction in planes. So it's exactly the same as before, but the added difficulty of dealing with an angled plane. This is our basic setup of a particle, body, whatever you want to call it, on an angled plane. It's got a massive m kilograms, so weight of mg. There's a reaction force acting perpendicular to the surface, got a friction, preventing it from going down the plane. If we look at the limiting situation where it's just on the verge of going down the plane, and we'll see what we can find out about mu. Now, as before, if that's theta, that's 90 minus theta. I've got theta here. Why is that useful? So that I can do this one is mg cos theta. And we can say that if we resolve that way, which is never going to be leaving the plane, so it's always going to be in equilibrium, I can balance the forces down and say that R is equal to mg cos theta. If I resolve up and down the plane, I've got friction equals mg sine theta. And if I use friction equals mu r, because it's on the verge of going, I'm going to say that mg sine theta equals mu times mg cos theta. The O and the g cancel out, so the mass is almost irrelevant to this situation here. And what I can do with this one, I've got sine theta equals mu cos theta. I can cross divide and get tan theta, which is sine over cos, equals mu. So in its limiting situation, the value of mu and the value of theta are linked. So if mu, for example, is 0.2, divided shift tan 0.2, the maximum angle will be 11.3 degrees. Anything less than that, we're going nowhere. Anything steeper than 11.3, we're definitely in motion. Bang on 11.3 degrees, the thing is in limiting equilibrium. If it's a higher value of mu, like 0.5, shift tan 0.5, means I can have a steeper angle because it's a bit rough. So 26.56, 26.6 degrees roughly means I can have more of an angle before it's just about to go. So the higher the mu is, the rougher the join between the two surfaces, and the more of an angle I can tilt it before we're off and running. I've actually done this lesson in school recently, and so example one says I've got a sledge of mass 8 kilograms. The question is find mu when on the point of sliding if the slope is equal to 6 degrees. And I said to my students, right, I've done it. And they said, what, that quick? I said, yeah. I said, not only have I done it, I've only pressed 3 buttons. And they asked, did that include the equals? I said, yeah. Because all I'm doing is just using this. We said if it's limiting, then tan theta is equal to mu. So how to find mu then? I just went tan 6 equals 0.105. So in this case here, I can just do what I've done over this side. I can draw it. The fact is mass of 8 kilograms was irrelevant because the mass cancelled out, the weight cancelled out, and I got that tan 6 degrees is equal to mu, which is 0.105 or 0.11. I wouldn't go beyond 2 figures because I haven't really used G. G cancelled out, so I've only got one significant figure values in here, so I'll be quoting 0.1 and 0.11 in that case there. Okay. Well, let's have a look how we apply it in different situations. Here's a situation here. We want to find the tension. In this case, we've got a I can't remember now. I haven't put a mass on, so I think we can only find the tension in terms of whatever the mass is. I'm not going to be able to solve it in this case here. I'm told mu is equal to 3/4, so quite rough. I've got the plane's an angle of 30 degrees. The tension is also an angle of 30 degrees to the plane. I've got my reaction. We want to find the tension of the things on the point of moving up the plane first. So if we're moving up the plane, my friction will be acting downwards. I'm going to put on then my T cos 30 in that point there. I'm going to put on down here mg cos 30 that way, so that when I resolve horizontally, along the plane and perpendicular to the plane, I can use these on or use the sine versions as appropriate. So let's have a look what I've got then. It's going to be very similar to what I had before. I'm going to resolve to find friction in terms of T, resolve that way to find reaction in terms of T, use friction equals mu r to get an equation with T and solve it. I don't think m is going to cancel out, so I'm going to be left with T in terms of m. So let's have a look what I've got then. So it might be a bit of a mess, this. Up the plane I've got T cos 30. Down the plane I've got friction plus the weight component. Well, if that weight component is mg cos 30, this is mg sine 30. I'm going to use the fact 30 is a standard angle. I know a cos is root 3 over 2 and sine is a half. I'll rearrange to get friction equals T root 3 over 2 minus mg over 2. I'm using the fact that sine 30 is a half and cos 30 is root 3 over 2. There. I'm going to resolve perpendicular to the plane to get r plus t. Well, if that's t cos 30, that one, this will be t sine 30. And that will equal no friction component, but there is a weight component, mg cos 30. So r will equal mg cos 30, mg root 3 over 2 minus t over 2. I'm going to use friction equals mu r. So friction is this mess, t root 3 over 2 minus mg over 2 equals 3/4 mg root 3 over 2 minus t over 2. And close the bracket. I've got a common factor every single term. I've got 1, 2, 3, 4 terms with over 2 in. That 3/4 is going to multiply and change it. But I can divide or cancel the chart by times and everything by 2. Do a little bit of cross multiplying to help me out. It's night. I'm going to have messes. It's going to be awkward. But what I'm going to end up doing is getting everything with t on one side, everything with mg on the other side. But it's nicer if I do 4t root 3 minus 4 mg, and it will equal 3 mg root 3 minus 3t. So in this case here, when I collect everything together, I'm going to make the t's over here 4 root 3 plus 3. On that side, mg times 3 root 3 plus 4. Because that one's going to cross become plus and so on like that. So t will equal mg times 3 root 3 plus 4 over 4 root 3 plus 3. That's my exact value. They get quite messy, these algebra at the end, but we need to sort of start off at that point there, do our resolving and see what happens. Oh, there was another bit. If it was on the point of moving down the plane, then my friction will be acting this way, and it would just change some signs. So it wouldn't alter the r value, it would be just the same, but when I did this one, I would end up with t cos theta plus my friction equals my weight. My weight would equal that there, sorry, minus that and plus that. And that would be the only difference there, so I'd have minus there and plus there. So I'd have minus 4t root 3 plus that. And when I move them around, I'd actually move that over there to get 4 root 3 minus 3. And move the 3mg root 3 over there to get minus 3 root 3. I'm panicking now because that's going to be negative, I think. There, 4 root 3 minus 3. So I'm getting the minus 3 root 3 plus 4 and then 4mg minus 3. Basically, it's just going to change some of the signs for some of the things there. So it would make the signs different at this stage because friction is acting in the opposite direction. It would make the value of t different because of this, and it would therefore make the value of friction different later on because it's acting in the opposite direction. Last one. You give me mu. It's a horizontal force. It's slipping down the plane, so on the verge of slipping down the plane. So my friction will act upwards. I'm going to do my component of F, and if that's theta, that's 90 minus theta. This is also theta, so that's F cos theta. But they haven't given me what cos theta is. They give me tan theta though. What I can do with it, I could do shift tan 3/4 to get the angle. What I'm going to do is do a little sketch, right angle triangle, theta there, do tan is opposite over adjacent, and then say by Pythagoras 3, 4, 5, we do that, and say sine theta is opposite over hypotenuse 3/5, and cos theta is adjacent over hypotenuse 4/5. And then we're off and running. I'm going to do as I've done before, resolve up the plane to get an equation with friction in, resolve perpendicular plane to get an equation with R in, use friction equals mu R, friction equals 1/5 of R. Each one will have F in, and do the same as what I did before. So resolve up the plane. Friction plus F cos theta equals, I forgot to put in W cos theta going that way, because that's from the picture. So going down the plane will be W sine theta. So what will friction equal then? It will be W times 3/5, 3W/5 minus F times cos 4F/5. There's my friction. Resolve that way in the same way. R going up will equal F, well if that was F cos that way, this will be F sine. And then plus W cos. So that equals F sine 3F/5 plus 4W/5. Then use friction equals mu R to get friction. 3W/5 minus 4F/5 equals 1/5 of R, 3F/5 plus 4W/5. Cancel the 5's out. Notice even though there's a 1/5 there, that's a different thing altogether, but we then cross multiply. 15W minus 20F equals 3F plus 4W. Move them across. 15 minus 4, 11W equals 23F. So F is 11W/23. So in that case there, I've resolved. I've got an equation with F in each one for friction and for R, so I haven't solved it as such. What I've then done is quote friction equals mu R, stuck in my equation for friction with F in, stuck in my equation for R with F in, get all the F's on one side and everything else on the other side, and then solve it to find what F is in terms of W in this case. And that's how we deal with friction and planes.